Hi, this is Rick Kolk, and today I'm going to discuss VisSim Embedded Modeling, Fundamental Concepts Part 2. This video will cover the following topics: the VisSim unit delay operator, modeling a discrete integrator, the merge and cross detect blocks, modeling a discrete integrator with reset, creating a repeating time signal, assigning names to compound block pins, and adding your models to the VisSim Embedded Menubar. The VisSim unit delay block, available under Blocks Time Delay, applies a zero-order hold to a signal. The unit delay accepts two inputs, a Boolean labeled B and a signal labeled X. The Boolean pulse input signal can be created in either of two ways. First, it can be set to a constant, 1, causing the unit delay to trigger every time step of the simulation. Second, it can be set using a pulse train available under block signal producers to define the time between triggers. At the left, I've created an example of both ways of triggering the unit delay. First, I've defined an input signal as time, a unit slope ramp, and applied it to a unit delay being triggered with a constant 1, and also to a unit delay being triggered by a pulse train, time interval set to 0.1 seconds. Our simulation is running at 1 millisecond. Executing this model shows the behavior of both ways of triggering the unit delay. In green, we can clearly see the effect of the zero-order hold, the hold plus the unit delay. For embedded applications, speed and memory space are critically important, and the discrete integrator is often the preferred method for integration. Here's an example of a forward Euler discrete integrator using the unit delay function. The unit delay is triggered with a 1 on the Boolean input, meaning that it updates every iteration of the simulation. $time step is a gain that's pre-multiplying the input signal. We can compare the behavior of the digital integrator with an analog integrator, and running this in parallel with our digital integrator, and plotting the results in the same plot box. You'll notice they lie on top of one another, meaning that the digital integrator is faithfully reproducing the analog integrator. We can modify our discrete integrator to a function that produces time by replacing the input signal and the time step gain with a constant set to time step. If I go under Block, Signal Producer, Constant, select the constant value to be $time step, and connect that in place of my existing input, I will have created a time signal. You notice the slope is 1. The merge and cross detect blocks are frequently used in models. The merge block provides the if-then-else function. When the Boolean to the merge block is true, the output is equal to the true input on the merge. When the Boolean is false or 0, the output is equal to the false input. Running this example, I can toggle the Boolean input with this switch, and you can see the output changing from true to false to true. The cross detect outputs a -1 when the sine wave passes from positive to negative through the cross point, and similarly a +1 when the sine wave transitions from minus to plus through the cross point. We can modify the discrete integrator we previously created with reset capability by adding the merge block. In this diagram, I'm using a merge block to reset the initial condition of a discrete integrator. I'm integrating a square wave, and as we run this, I will periodically reset the integrator. You can see that I'm resetting it to its initial condition of 0. The discrete integrator with reset is used frequently enough, it makes sense to put it into a compound block, which I've done here. Within the compound block, I have 3 inputs, the input, the trigger, and the reset value, and the output is produced then. I can label the pins by double-clicking input, trigger, and reset value, and I can label the output as well. We can confirm the operation by connecting this to our input signal, our trigger, and our reset value, and overplot it and run it with the original diagram. And as I reset the integrator, you'll notice the blue line, which is plotted second, so it's overlaying the red line, showing that both are producing identical results. The function y equals sine of 6t uses elapsed time as an input. Embedded models are designed to run forever, and if this function were implemented using t, it would eventually overflow. To prevent this, a repeating time signal, which repeats itself each cycle of the sine wave, is constructed using a discrete integrator with reset. The input to this model will be a frequency in radians per second. I will place a constant block and a label to denote that. Next, I will convert the radian per second frequency to a hertz using a gain block, and the gain is set to 1 divided by 2 times pi. Now the output of this block will be cycles per second, or hertz. Now if I multiply this output, cycles per second, by time, which I will obtain as the x of t signal, the result will be a normalized fraction of a cycle. That is, a value that will range 0 to 1 as a cycle evolves completely. I'll need to manipulate the diagram slightly to make this happen. So let me get rid of some labels and complexity here. And we'll move the diagram over to the right. We'll get rid of that. And place this here. We may need this later. And we'll attach time to the other side of the multiply. Now this output signal right here will be normalized time. That is, it will be a value that ranges from 0 to 1 as the sinusoid goes through one complete cycle. So I'll capture it in a variable named time normalized. And what I will do is pass this through a cross-detect block located under block nonlinear, with the cross-detect point set to 1. So as soon as this t normalized reaches 1, the cross-detect will trigger, and I'll use that to trigger the Boolean on my merge, which will reinitialize time to begin counting again from 0. Let's take a look and see how this behaves. I'll get a plots box, place it on the screen, and I will plot out t normalized. And I will also plot out what will become our repeating time signal, which is this signal here. I'll call it t repeating. And we'll plot that in a separate plot box right underneath it. I have the frequency set to 1 radian a second, which means that it will take 6.28 seconds per cycle. As I run this, you see the t normalized ranges from 0 to 1 and resets itself at exactly 6.28 seconds, and I can see that by looking in the crosshair value. And the t repeating is a time value now. Its amplitude is time that goes from 0 to 6.28 seconds, at which point it repeats itself, reinitializing at 0, and again going from 0 to 6.28 seconds. To complete the implementation of y equals sine of 6t, I'll need a multiply block under blocks, arithmetic, multiply, and I will multiply the input frequency times t repeating. I need a sine block, which is located under blocks, transcendental, sine. And that will produce my output, which I'll label as y. Simulate this and see how y behaves. I will plot y in the top plot and get rid of t normalized. And we'll run it again. We're running at 1 radian a second. So we see the cycle evolve in exactly 2 pi seconds. Let's try another frequency. I will reset the 1 radian a second to 3, resimulate, and the sine wave is behaving correctly. It's evolving now at 3 radians per second. Let's try 6 radians per second, which should just about give us 1 hertz. And we see again the sine wave behaving correctly, and t repeating is repeating at the correct period. In some situations, you will want to create your own folder of models and have them available as a drop-down menu on the VisSim toolbar. For example, we will create our own drop-down menu called My Models, and within it I will create one subfolder called Signal Generators. After using Windows File Explorer to create the My Models folder and the subfolder Signal Generators all in the VisSim 90 folder, I will launch VisSim, go to Edit, Preferences, Menu Directories, and go way to the bottom, click on the ellipsis, and this is where we define where our models will be located. So the first thing we need to do is to browse to the model folder. So this is under VisSim 90, My Models, Signal Generator. Hit OK. Open as new file. Well, we don't want that. We want to be able to add these to existing diagrams, so we'll uncheck that. We would like to include VSM files in subdirectories, so we'll include that. And I will give this a name. I'll call it My Models. This is the toolbar name. Hit Set, OK, and we're done. Now I'll need to relaunch VisSim. So I've relaunched VisSim, and we can see My Models folder is now available with Signal Generator and repeating time in it. I can place it on the screen as many times as I want. And that's how you create your folder of models. Thank you.